Hello everyone and welcome back to Techmine Guru. I'm your coach Supratim and today we are diving into DSA lecture 19. We are demystifying recursion. If you have ever felt intimidated by recursive functions, don't worry. By the end of this video, you will know the 3-step framework to solve any recursive problem. Before we jump in, let's look at our agenda for today. We are going to cover 4 main areas today. First, what is recursion? Second, the 3-step framework for the recursion. Third, how the call stack work under the hood, and finally some classic interview problems to put it all together. So what exactly is recursion? Simply putting, it is a function calling itself. So when a function calls itself, a large problem is broken down into smaller subproblems. Then by using the solution of these subproblems, the main problem is solved. To make writing recursive code as easy as possible, I want you to follow these 3 straightforward steps. Step 1, define the problem and the function. Step 2, define your recursive relation. Step 3 is to define your base case, which is the simplest version of your problem. So let's see the 3 steps in action with our first example, finding the sum of first 10 natural numbers. So for example, you have to express sum of 5 is equal to 1 plus 2 plus 3 plus 4 plus 5. So if you closely observe from 1 till 4, this is you can express as sum of 4. So sum of 5 will be sum of 4 plus 5, right? Similarly, if you express in terms of n, the sum of n will be equal to sum of n minus 1 plus n. So let's see the 3 steps in action. So suppose this question is given finding the sum of first 10 natural number. So step 1 will be express this 1 plus 2 plus 3 up to n to a function named as sum of n. Now in step 2, we will write a recursive relation. So what is a recursive relation? Sum of n is equal to sum of n minus 1 plus n. And in step 3, we will write the smallest base case, which is sum of 1 will be equal to 1 only. So the base case where the loop will stop. So if you see the code in sum of n, the base case is written as if n is equal to 1, return 1. Otherwise, you have to return sum of n minus 1 plus n, which is the recurrence formula which we are getting from this step 2. So let's understand that what is happening under the hood with a simpler example. Suppose code is given with x is equal to 10 and y is equal to 20. And you have to do add of x comma y. Then the result which you will get, you have to multiply it with the 30, and the final result which you will get from here, you will subtract 75 from it. So when you call the print function will internally call the subtract function. The subtract function will internally call the multiplication function, and the multiplication function will internally call the add function. So in the add function, you will see that you have x is equal to 10 and y is equal to 20, and this will give the result as 30. Once it gives the result as 30, this 30 will be coming here as it is the result of add of x comma y. So when you do multiplication of 30 comma 30, this will give us the result as 900, right? So this 900 will be passed here, and this 2 will get removed from the stack. Now in the subtract function, we will subtract 75 from 900, and finally we will get the result as 825. And as soon as this subtract function does its job, it will also remove from the call stack, and the control will come to the print function, and the print function will give the result as 825. So let's see the next example. So you have to find the factorial of n. So for example, 5 factorial will be 1 into 2 into 3 into 4 into 5. Similarly, if you see for 4 factorial, it will be 1 into 2 into 3 into 4. So if you have to write the recurrence relation of this, what you will write? Fact of n will be equal to number itself, which is n, into fact of n minus 1. So in this case, factorial of 5 will be equal to 5 into factorial of 4, right? But you have to define the base case here. So what is the base case? The base case will be when the n will be equal to 0. So if n is equal to 0, we have to return 1. So we know that factorial of 0 is equal to 1. So that this will become our stopping point. And simply whatever you have derived the recurrence relation, you will simply return that as a final result. Int of fact, int n, if n is equal to 0, return 1, else return n into fact of n minus 1. So if you don't use this base condition, this will go into a stack crash loop. So what may be happening under the hood? Let's see that. So this factorial of 3 can be expressed as factorial of 2 into 3, right? So the call will move to here. Then factorial of 2 will express itself as factorial of 1 into 2, right? Then factorial of 1 will be expressed as factorial of 0 into 1, right? And we know that factorial of 1 will be returning 1 as the answer. So when it will return 1, this thing will get the result as 1. So 1 into 1, this will be 1 only. So this fact of 1 will be 1 now. Now, since we got the fact of 1, we can keep the value fact of 1 as here. So 1 into 2 will give the fact of 2 value. So since we have got the fact of 2, the fact of 2 will be 2 into 3, which will be 6. So result will be 1 into 2 into 3, which is equal to 6. Moving on to level 3. Let's look at execution order and how placement changes everything. So you have been given n. We want to print numbers from 1 to n. So if you have to print numbers from 1 to n in increasing order, and if you have to print in decreasing order, the placement matters a lot. So suppose increment of 5 is given as 1, 2, 3, 4, 5. So what will be the recurrence relation? Increment of n will be equal to increment of n minus 1 and then n, right? Similarly, if you see the decreasing term, decreasing of 5 will be equal to 5, 4, 3, 2, 1. So what is DEC of 4? It will be 4, 3, 2 and 1, right? So if you write the recurrence relation, DEC of n will be equal to n and then DEC of n minus 1. So the placement of n is getting changed. So let's see that in the code. So increment of n, if n is equal to 1, you have to print 1 and you have to return. So let's see that with increment of 5, right? So increment of 5, we'll see that n is 5 or not. 5 is not equal to 1. So it will come this line. It will again call increment of 4, right? Increment of 4 internally will keep n as 4 and it will check 4 is equal to 1 or not. It will again call increment of 3, right? Similarly, increment of 3 will call increment of 2 and increment of 2 will finally call increment of 1 and there n will be equal to 1. So it will print 1 here. So when it will print 1, suppose it prints 1, then you are in the increment of 2 loop. Then you have to print n. So you will print 2 because in this increment of 2, n is equal to 2. So when this is printed, your code will move to increment of 3, right? Because increment of 2 is done now. So it will print the number 3. As soon as it is printing the number 3, increment of 3 will be over and the control will come to increment of 4 because increment of 4 only called increment of 3, which is over, which has printed till 3. This increment of 4 will print now 4 and then finally the control will move to increment of 5 and where 5 will be printed and the execution will return back to its main function. Similarly, if you see the DSC, the print is before the recursive function is called. So if you see the call chain there, decrement of 5 will call decrement of 4, decrement of 4 will call decrement of 3. But in this, suppose decrement of 5 is getting called, it will check if 5 is equal to 1 or not, it will return false. It will print 5. It will print 5 and then decrement of 4 will be called. Similarly, decrement of 4 will check here 4 is equal to 1 or not. It will print the number as 4 and then it will call decrement of 3. Similarly, decrement of 3 will see whether the number is 1 or not. It will print the number as 3 and then it will call decrement of 2. This decrement of 2 will print 2 and it will call decrement of 1. Finally, we will see that 1 is equal to 1, it will print 1. So if you see here, if you have just put the print statement before calling recursively, it is printing like 5, 4, 3, 2, 1. But in this case, in case of increment, we have to do the recursive function first and then we have to print it. So now let's understand how we can calculate the time complexity in case where recursion is there. So the simple formula is time complexity of any recursion will be equal to O of number of function calls into time complexity per function call. So if you see the above example, so what is the time complexity of one function call? It will be O of 1. But to print 5 numbers, how many recursive functions has been called? 5, right? So if for n, how many it will be? N, right? So n will be number of function calls and time complexity per function call is O of 1. So in short, it will be O of n only. And how do we calculate space complexity in this case? For that, we have to find the maximum depth of the recursion tree or stack. And then you have to add it with space complexity per function call. So if you do analysis of that increment, decrement and factorial, the total function calls will be n plus 1 and max stack size will be n plus 1. And time complexity per call is equal to O of 1 only. So what is the total time complexity of above 3 problems? The factorial, increment and decrement is O of n. And since each function is calling recursively n plus 1 times, so the space complexity is O of n only. Because in every function, you can see the space complexity of that individual function is O of 1. So it will be O of 1 plus the recursion stack length is n, which is O of n plus O of 1, which is O of n only. So now let's see the last problem of our day today, which is the Fibonacci series. So let's understand the Fibonacci series. The Fibonacci series is that every term is the addition of previous 2 terms. So if you see, so it generally starts from fib of 0 as 0 and fib of 1 as 1, then we can get the next term. So what is the second term? It will be addition of fib of 1 and fib of 0. So 0 plus 1 will be 1. So what will be the fib of 3? It will be fib of 1 and fib of 2. So it will be 1 plus 1, 2. Similarly, what is fib of 4? It will be fib of 3 and fib of 2. So it will be 1 plus 2, which is equal to 3. Similarly, for the next one, 3 plus 5 is equal to 8. And the next term, 8 plus 5 is equal to 13. So in the step 1, we have to find the nth Fibonacci number, right? And when you want to write the recurrence relation, it will be fib of n is equal to fib of n minus 1 plus fib of n minus 2. So basically, there are two terms. So you can think whenever there is two terms in a recurrence relation, you have to think the base case for both of them. So what will be the base case for Fibonacci? Fib of 0 will be equal to 0 and fib of 1 will be equal to 1. So in this, we have simply wrote the code for the same. So if we have n is equal to 0 or n is equal to 1, we will return n. So suppose 0 comes, it will return 0. So suppose 1 comes, it will return 1, or else it will be fib of n minus 1 plus fib of n minus 2. So let's understand that with the recursion tree. So suppose you have to find out the fib of 4. This fib of 4 will call fib of 3 and fib of 2, right? So your control will come here in the fib of 3. So fib of 3 will again call fib of 2 and fib of 1. Now again the control will come to fib of 2. The fib of 2 will call fib of 1 and fib of 0. And since these are the base condition, it will return result as 1 and 0. When we get this result of fib as 0 plus 1 as 1, we will now jump back to the fib of 1. The fib of 1 will be our base condition. It will also return 1. And what does fib of 2 return? It also returned 1. Now we have the value of fib of 3. When fib of 3 is done, then we will go to fib of 2, right? Fib of 2 will again call fib of 1 and fib of 0. So they are again base condition. Fib of 0 will return 0. Fib of 1 will return 1. So 0 plus 1. So the fib of 2 will return 1. And fib of 3 is already having 2. So now the fib of 4 will have everything from fib of 3 and fib of 2. So it will return 2 plus 1 as 3 as the result for the fib of 4. So it is like when your recurrence relation is given and your code moves here, it will go to this stack first, and once it comes out this one completely, then only it will start going to this respective one after the addition. So let's understand the call stack here. So fib of 4 called fib of 3 and fib of 2. Fib of 3 called fib of 2 and fib of 1. Fib of 2 inside will call fib of 1 and fib of 0. So first of all, 3 will come, fib of 3 will get called. It will internally call fib of 2. It will internally call fib of 1. And when it will return the result to fib of 2, then that fib of 2 will call 1 again, right? And then when both are finished, then only fib of 3 will give the result. Then when the fib of 3 is over, it will again call fib of 2 here, which will again call fib of 1 here and fib of 0. Since both of them will give the result as 1, so fib of 2 work is also done. So our call stack is this much only, which is 3 in length. So let's try to find the time complexity of the same. In the level 0, you will have 2 to the power 0 calls, right? Similarly, in the level 1, you will see 2 to the power 1 calls. In the ith level, it will be 2 to the power ith call. So it is following a geometric series. So what is the sum of geometric series? As we have already learned, it will be a into r to the power n minus 1 divided by r minus 1, right? So what is a here? 1, r is 2, n will be n only, then 2 to the power n minus 1 divided by 2 minus 1, which is again equal to 1 only. So the total time complexity will be O of 2 to the power n. And for space complexity, we have already understood that the call stack now only holds the current active path from root to that leaf node only, and not the entire tree. So what is the max depth of that tree? Which will be equal to n. That is, max stack size will be equal to n. So our space complexity will be O of n only. So let's wrap things up with our summary and golden rules. So you have to trust the recursive leap of faith. Know that your sub problems will be solved. Never forget your base case or you will crash the call stack. Third, your max depth should be equal to your space complexity. That is all for today's class. In our next lecture, we will be tackling some real interview problems on recursion. If you found this helpful, please like and subscribe, and I will see you in the next video. Till then, keep coding, keep learning, and keep optimizing.